quick word before we start. So the slides are not up. Okay. Can someone? Okay, cool. So the slides are available at that link. So that would be s.apache.org/streaming-python-beam-flink. There might be some technical details that we skim over, but that are in the slides. So if you want to check out the slides, you can go to that link. Also, this is not okay. So today, we're going to quickly talk about what Beam is, then what the purpose of these portability APIs is, then how we use those to execute Python jobs on Flink, and then we're going to have a short outlook what still remains to be done with this. The problem that we are facing and that we are trying to tackle with this work, along with a lot of other contributors to the Beam project, is that a lot of projects in this big data ecosystem, they are Java-based, so you have to use Java to write your pipelines. But many other communities of developers, they like to use different languages. So for example, machine learning folks, they like to use Python because it has all these nice Python machine learning libraries like SciPy. And the barrier of entries for those teams is quite high if you simply cannot use Python for writing your stream processing pipelines or batch processing pipelines. Looking back a bit, this is somewhat funny, because I had a talk at last year's Flink Forward called Talk Python to Me that had a very similar looking title slide. It's the data artisan green, not the nice blue. And most of the content of the technical details is actually the same, but at that time we didn't have a working demo. But today we actually have a working demo that we can show. And the work on this started way back in 2016. There was a Python SDK available for Dataflow. So Dataflow is the managed service by Google on which you can run Beam pipelines. And in this talk, we are mostly talking about Python, but almost always when we say Python, you could also insert Go, because there's also work on adding support for executing Go pipelines on Beam via this portability API, but here we mostly say Python. So now quickly, some people might already know what Beam is, but I want to recap so that everyone is on the same page. Beam is a unified model, if you will, for describing batch and stream processing pipelines. And along with this model, there come SDKs in different languages that you can use to write those pipelines, to write user-defined functions, to wire them together. It is a set of runners for executing those pipelines. So there's a Flink Runner for executing Beam pipelines on Flink. There's a Google Dataflow Runner. And it's a collection of I/O connectors for reading data from some sources, like from Kafka or from Kinesis, and writing it to, say, Bigtable. And the vision for Beam from quite early on is that we have this unified model that describes what pipelines look like, but that users should be able to write these pipelines in different languages. And they're all used to construct pipelines for that model. Then there would be different runners, say, as I mentioned, Flink, Dataflow, Spark, and so on. And they use some API abstraction to execute those user functions written in different languages. The Beam model is you basically construct a graph of operations. So these would be sources, these would be sinks. In between, you have operations. So that would be, for example, like a map function. We call them p-transforms. And those arrows, so the things that represent data, which in Flink we call DataStream or DataSet, are called p-collection in Beam. Yep. In Beam, when you write pipelines, there's a separation of concerns, if you will, about the different parts, or different words that you think about. So there's the question, what should be calculated? Where in event time should it be calculated? When should the results be produced? And how do refinements relate? So we will quickly walk through what that means in practice. So here on the top, I always have the Java code. On the bottom, I have the Python code. So for this talk, maybe the Python code is more interesting. But what we have here is we have an input, which would be a P collection. Then we do this shell-like pipe and apply a P transform that says some integers per key. So we have some key value of string and integers, and we want to sum all that that have the same string key. So this is what we want to compute. So this just says how we compute all the data that we have. We don't consider event time or processing time. The next question is, where in event time do we want to compute these results? So this is what traditionally in Flink we call windowing. Beam also calls it windowing. So we now say that instead of just computing the sum of these integers per key over everything, we say we want to partition our event time space into windows. And so we say we want to window it into fixed windows of, say, 2 minutes. So with this, we compute results for these 2-minute windows. The next question is when we actually want to receive that data. So the when only says where in time we want to split that data, but the when is what in Flink we call triggering. And here in Beam it's also called triggering. So here we say we want to get those results when we get the watermark. The watermark is this heuristic that tells us within reasonable bounds whether we have seen all the data up to a given timestamp. So with this, we have our computation, the what we do, we split it by event time, and then with the watermark triggering, we say when we want to get that data. So that green line here is the watermark. So when that reaches processing time, we get our results. And that line up here would be a late event for those interested. The last bit is the how. This is somewhat tricky. It basically says if we have multiple firings, so if, for example, we want to have a result when the watermark arrives, but then we want to consider late events also and still include them in the computation, then we have to say how those different firings for the different trigger firings relate. And that we do by saying we want to accumulate those the results. So if we want to keep adding to that sum, or when we fire once, we should throw that away. So we would be discarding the fire panes. And each firing would be the sum since the last firing, basically. So with this, we now see that we have firings that are early or on time, and for this 9 up there, we have a late firing. And we are accumulating the results, so it's 14 and not just 9. At the end, I want to quickly show what a complete pipeline in Pythonic Beam code looks like. So people that know Python might find this pipe construct a bit weird because it's not really Pythonic, but the Beam folks, they did a lot of different iterations, tried out different things, and in the end, this shell-like pipe character seemed like the most reasonable thing to do. And here what we do is we read from a source, we window it, we map something, then we sum up per key, we map it to some format that we want to write to BigQuery, and then we write it to BigQuery. Just quickly mentioning what runners exist. So recently there have come up quite a few runners. So obviously the obvious runner is Google Dataflow. So this originated at Google, and the Google Dataflow runner was the first runner. Apache Flink was one of the first open source runners, and arguably, I think Thomas has a matrix of compatibility later. It's one of the most feature complete runners, I would say. Now, I talked about this at the beginning already. We have this nice Beam model abstraction. We can, in theory, we can use Java for that. That was the original thing in Beam. But up until recently, you couldn't actually run Python pipelines on the runners that were written in JVM. So you couldn't, for example, use TensorFlow to work with Beam pipelines. And you couldn't combine, for example, connectors that are written in Java with a connector written in Python. And that is the actual vision of Beam. And now we are quite close to that vision. And Thomas is going to talk about how that vision is implemented, that vision of running multiple languages on different runners.
Yeah, thanks, Aljoscha. So let's get to the portability part. Visual recap, what is it that we are trying to achieve? So transforms can be written in multiple language SDKs. Beam has SDK, as Aljoscha said, for Java, Python, Go, and there may be others in the future. We need a way to execute this code that is written in a language of choice on any runner. For that, we need a portable pipeline representation that each runner can understand, and the runner needs to have a way to execute the Python code. Let's say it's Flink, it's a Java runner. It needs to have a way to execute Python code in a way that is natural to the Python programming environment and ecosystem. And this, it cannot be just a UDF, like simple sum, like in this case, it could also be an I/O connector. Typically, there's a lot of work that goes into I/O connectors, and today the Beam Java SDK has a broad range of connectors, but they are not accessible from the Python SDK. And Python SDK currently does not have any connector for streaming. It does have for batch, for reading files and writing files, but not yet for streaming, except when you run on Dataflow. So this is what we want to accomplish. How does the portability framework look like? You have on the left side the user and the SDK. And you would like to submit a pipeline. In the case of Python, it would look like this. When you have the word count example, there are a few extra pipeline options that specify where to run it, on which runner. Other than that, it's the same pipeline code that would also run on the Python direct runner. Here we are specifying that we want a portable runner and an endpoint. So the job service endpoint is what, for example, the Flink job service provides. This is specific to a runner, in this case to Flink, and it exposes a service that can be used to submit a pipeline and to check status of a pipeline too. In addition to the pipeline that is being submitted, it is also possible to stage artifacts, which can be used to specify dependencies, like Python packages in this case. It's not shown here, but it can be done, that are then made available through a staging location to be retrieved later by an SDK harness. So once the pipeline gets to the job service, it's the runner's job to translate it into a native API. And in the Flink case, there are two native API where translation occurs today. It's DataStream and DataSet, depending on whether this is a bounded or unbounded pipeline. On the Beam side, notably, there's no such differentiation. The example that Aljoscha showed you, it would execute in batch or in streaming without modification. It's just that the type of source determines whether this is a batch execution or streaming execution. So, but today in Flink, we still have the distinction between batch and streaming here in the runner, so there are separate translations. At the end of the translation, we have a Flink job graph that can be submitted like any other Flink job to the cluster. And the only difference between the Flink cluster that you might know from your Java Flink jobs and what you would have when you run a Beam Python pipeline or any Beam portable pipeline is that there are additional processes in this cluster, and they are necessary to execute the user code. So what you end up with really is you have Python here at the front, and then it goes through the middleman, and you end up with a Python process in the Flink cluster, because that's the only way, the only generic correct way to run Python. There are other approaches like Jython and so on, but none of those really work for everything. To run Python properly, you want to be able to use all your libraries and everything, and this is being done by having a native Python process that would run in the task manager environment. There are different options to execute, we will cover later. The interaction between these Python worker processes and the runner, so the Flink task manager in this case, is governed through interfaces. The runner exposes endpoints that the SDK harness talks to perform its function. More details will come. So the following slides, there will be some details that we don't have time to cover here, but most of the slides have a link that points to the Beam documentation that covers all of this in detail. So you have access to the slides. You can later look up all of these things and read up about this. So important APIs in portability is Pipeline API. Pipeline API is essentially a description of a pipeline that is language agnostic. Like you would find in IDL and other systems. It can be translated into language bindings, but it's a proto-above definition. And this is used by the SDK to build the pipeline that is wire compatible with any runner. We also call this a dehydrated pipeline, what goes over the wire, and can be used by the runner to reconstruct rehydrate the pipeline, to introspect it, and then to build its native representation. The job API is what we saw where the pipeline is submitted to the endpoint. The FN API is where the runner and the SDK harness communicate with each other to get the real work done during execution. So simplified pipeline, how does it look like? It's really a collection of P collections, transforms, windowing strategies, coders. So the disassembled pipeline, if you wish. And the interesting part probably is how do we represent the language-specific parts. So you see the function spec. It could be a Java do-fun, which is serialized object, or Python pickled function. That's the payload. It's language SDK specific, and then a URN that says what it is. And later on, the SDK can look at it, and it can deserialize it. And the runner doesn't need to look at it because it cannot read it, and it doesn't need to. So bundle processing, the control plane and the data plane. A bundle is the unit of work in Beam. Bundle can have many elements. If it is a batch pipeline, it can have just one element. If it's a streaming pipeline, in the case of the Flink Runner. To process a bundle, the runner tells the SDK process or SDK harness what kind of functions are required to execute the bundle, and then that it should start processing a bundle. The SDK harness then will turn around and will start to get the input elements for the bundle, and it will also give the output elements back to the runner. And then at some point, the bundle processing ends. Details in the linked document. For the data, the interesting part here is that the encoding and the decoding happens on the SDK side and not on the runner side. The runner side, for runner side, the elements are opaque, except that the runner, for certain things, needs to know what the key is. But other than that, the values, the runner doesn't need to understand. They are opaque and they are passed on to the SDK harness. SDK harness via gRPC. The SDK harness will decode elements, process elements, encode, send it back to the runner. Now, this is logical that something goes from here to here, from here to here. The gRPC is initiated always from the SDK harness, and it's reverse essentially. It's the runner that is driving the processing really, but the RPC is initiated from the harness, which gives it more flexibility to just orchestrate the system. So state API, kind of similar to data. The harness asks for certain pieces. The state API is needed because state is managed by the runner. Harness process is stateless, essentially. And the runner is responsible for holding the state. Like the Flink runner has to checkpoint the state, has to serve the state when a function needs it, if it's a stateful Pardo, for example. Harness can cache values to optimize, but generally the state needs to travel from the runner to the harness and back when it is mutated. Timers, not yet implemented. There's core support. Python SDK is about to add the timer support and the state support, user state support. The way it will work from a runner perspective, the runner exposes timers to as a special P collection. Timers that are due for processing will be streamed to the harness as part of the bundle processing. Timers that are scheduled for future processing will be streamed back like results from the harness to the runner. And then again, Flink is responsible for maintaining the state for it. So let's look how a portion of this pipeline would be executed. So you have what is called an executable stage. The equivalent in Flink would be an operator chain. It's functions that are fused together. So this is done by Beam. And Flink has really nothing to do with it. The Flink runner gets an executable stage and hands it over to the SDK harness. SDK harness will rehydrate the subgraph, wire it up, and then execute that stage. So it could be 2 Python map functions in such a chain. And when everything is orchestrated by the runner, there will be a gRPC source in front of the chain, and the gRPC sync after the chain logically, according to what I showed you before, which then makes it possible to process bundles on the SDK harness side. So for the execution, a little bit more about how the SDK harness is deployed or as a process. In Beam, we have what we call environments, and the default environment for SDK harness right now is Docker-based. So you can, all the Python code, SDK, and other Python packages would be already assembled into a Docker container. At runtime, the runner or Flink would spin up the Docker container when it is needed, and it would, of course, stay up. We don't do it on every bundle. It's a one-time thing. It will be reused. But then do the bundle processing repeatedly with the process running in the Docker container. Now, this is a nice generic way and will support many environments. In some situations, like we do at Lyft, we don't want the Docker container because we have an environment already where all the dependencies are already provisioned. We have Python virtual environment on our worker machines, Flink worker machines. So we have a different implementation to spawn the process directly. There's a Jira number there. This will be available in Beam too in the future, so direct process environment. And there's a third option that we only use for testing at the moment, but it's when the SDK language and the runner language are the same, like it is with the old Flink runner, and in the case of the Java SDK, then it would be possible also to execute the SDK code inside the runner itself, so inside the task manager. Would be an optimization with some efficiency gains. So there would be a repository of containers. Beam provides container for every language. Java, Python, Go. The default container is generic. It doesn't contain user code. There are 2 options for you to use that. You can either derive your own container from it and add your own dependencies into it, and it's self-contained, and you can specify the container when you launch a pipeline, the container image to use, or use the generic container and just inject your own dependencies via the artifacts or artifact staging mechanism in the Portability Framework. So what's the Flink what's the runner doing? Recap. So runner provides the job service endpoint for pipeline submission from Python for the user. It translates the pipeline into the native API, in the Flink's case, DataStream or DataSet. It provides the gRPC endpoints for the SDK harness to connect to. It is responsible for managing the SDK harness processes in first place, i.e. launching process or launching Docker or launching process directly, whatever the mechanism is. Then the runner will drive the processing. So it will request the harness to process bundles that contain the user code or that identify the user code. And the runner is responsible for managing the state, which is needed for side inputs and for user state and timers. Okay, so a lot of that code is common between runners. It's implemented in Java FN execution package. And what's specific to Flink Runner? Job server packaging, pipeline translators for the API, side input handlers, user state and timers in the future, and the way we finally launched the job on the Flink cluster, which is same as for the old runner. So comparison or pros and cons, the goal we set out to enable the execution of different language is achieved with the Portability Framework, isolation of user code, configurable execution environments, and also in the future the ability to mix code of different languages. The price, some RPC overhead because we have an extra process. Docker, the pros and cons of Docker. For many users, the cons or the advantages will overweigh. And then it's still early. We have at MVP for Flink now. It's a good time to check it out and to experiment, but it's still early adoption right now for this portability framework. Roadmap. Phase 2 would be that all features are fully supported, that all the validate runner tests pass in Beam. There's a test harness that verifies the functionality. Then next phase would be performance, and lastly, cross-language support. Feature matrix, we have in Flink good support now, and Flink is the only only one of the runners that Aljoscha showed earlier that supports the portability framework right now, besides Dataflow. So good support in batch and streaming already. A few features left to do. But we want to show you what works so far. So everything that is part of the famous word count demo is supported by now, which includes group by key, side inputs, and so on. So to do that, I will launch the Flink cluster here, and then just run the word count.
Ooh, that's small.
Okay, so we got the cluster. The next thing that we need is the job server. So we need the job server endpoint. And I specify where the Flink master is when starting the job server so that it knows where to submit the job. So now that is ready and listening. And the last step, if you are in a development environment, there is a convenient Gradle task to do that. But I wanted to show you how the Python command line looks like. You see these options that I mentioned before being passed to the Python process with the portable word count example application. So when we run this, we will see some activity first in the job server, because that will build the Flink application, and then that will go to the Flink cluster. So if I go over to Flink now, then we should see something happening here. Yes, so the application is processing, is finished, because it's a very small input file that I'm using. And so we could see the job graph now. So you might think it's a lot of operators when you compare this to how the word count would look like otherwise with native Flink, and that is correct. Now, something to note here is that the write write transform in Beam is quite comprehensive. It covers a lot of different scenarios on how files should be written, how they should be named, and that's why there are a lot of different paths here in the job graph that are not all used in all scenarios. The broadcast streams, and these are side inputs here. And inside these operator names, you would usually find, not recognizable here, I guess, also the environment name, i.e. the Docker container name. So that was just to show what works right now as of MVP, right? So going back to the slides. Oh no, I forgot one important part. We should also check that this actually did something. So if I go now here, I should see the Docker container still running. And then I can go into that Docker container. Okay.
You have to add bash at the end.
It would be good to have something to run too. Yes. So and the files, they were specified to be written under TMP and py something. Yes. So there are some counted the words of etc profile file. So that's not very exciting. But what is exciting that this entire system with all its bits and pieces is fully integrated and working now. It will be probably this will be available in a release probably in 2.8.0. This is right now the master branch in Beam. So future work, support for state and timers to make this feature complete. Mixing and matching connectors in different languages I think is very important in the long term. At Lyft, we are one of the early adopters for this, and we are contributing to this in Beam. We are going to initially use actually Flink connectors with custom URNs as the input sources for the pipelines. Then other SDKs, as they appear in the future, they should just work with the existing runner infrastructure. And on the Flink side, I think what would be nice, which would really simplify the implementation of the runner, of the Flink runner, would be if there was this common unified API. And it came up several times already at the conference. So I'm hopeful that something is going to happen in the future, and we will have less versions of translators to maintain in Beam. And then the Flink runner, I think. We need to think about the compatibility stories as Flink versions change in the future, the underlying Flink versions, but also how the pipelines become upgradable. If it changes in the pipeline, then can I still resume it from the state? These are similar problems that you as a Java Flink user would have with Flink's API. They apply for Beam pipelines too that are written in different languages. Yes, so that was it. I hope we have some time for questions. And companies are hiring, so we do, and so does Data Artisans. And we have some time for questions, I hope.
Yep, I think so, yes.
Hi, it's great work, but I'm curious, what's the performance impact of, for example, running on the Python process than in Java?
Well, so that's the most common question, right? Yesterday was a talk, and Robert gave some numbers, and there were some investigations made just based on a almost no-op Python function, and the overhead wasn't that large in that specific. I believe it was some 10% or something like this, right? 5 or 10%. Of course, that's a benchmark, right? A specific benchmark. And at the end of the day, you want to measure what it means for your application. So if your application runs complex Python code, right, then that amortizes you. The gRPC overhead won't matter that much. Then compared to Java, if you compare it with Java, it's like apples and oranges because Python execution is already slower than Java. So there is that the SDK itself is slower. So I would say it's feasible, I would say, The value is really that you can actually enable use cases that you couldn't do previously with a small cost. So that's how I would characterize it.
Yeah, my question is, how many of these SDK processes are running? Is it one per operator, or?
So yeah, that's also a good question, because there's a trade-off too between the parallelism that you can achieve and the resource utilization on the machine. So there's not one right answer. Right now, the way this is set up, I believe there are parallel worker threads on Python. If it's streaming mode, I think there are 12 or 16, and if it's batch mode, there are fewer than that, but you can actually control that. So for a single Python process, you can control the parallelism, and then something that we are going to do is that you can also control how many harness processes, not just threads, but harness processes run on a single task manager. So in my opinion, it should be the user's choice. If they understand their application best, if they say every task slot in Flink, it's a heavy computation and I really want separate process for each, then that should be possible. But if that's not the case, you can also run serve many different task slots in one SDK process.
Hello. So you addressed some of the performance concerns like from the CPU time, but what about like memory and space? Because from what I've seen, you copy the state over, and for instance, if I have a big map state, do you copy the entire map, or do you copy just the keys that get accessed, or what's the story with state?
Yes, so the answer is that technically the SDK harness could be completely stateless, and it can, for every state access, it would do a call to the runner and get the result back, then update it, and then send the update back. So that's the naive way, where you have no memory, basically, except for the overhead of the Python process. But the harnesses, they do some kind of caching, but I don't currently know how exactly that caching is implemented, because I'm working on the runner side, and the nice thing is that I don't have to know about the harnesses, and there's different harnesses. For example, the Go harness might do things differently than the Python harness or the Java harness. But yeah, in theory, it can be stateless, but it does some caching. That's the rough answer. Maybe you have some clarification.
Same, and then right, if it's a map state, then it should be possible to optimize it just to get the keys that are needed and not the full state blob, just like it is in a Flink application. The only difference is it has to go over the wire. Yeah.
But for map, it would only be that single thing being accessed, not the whole map.
Yeah, I have a use case of real-time classification. The data scientists developed a model today using scikit-learn and Python, and they want to push that code into production. Would you recommend to use that approach with the Beam runner for deploying that code, or do you have any other recommendation?
You're the person doing stuff in production.
Well, we are not. We are hoping to do. I mean, there is the way I would say. I mean, you have to be prepared to roll up the sleeves if you use it in its current state, the portability implementation, and there will be kinks to be worked out. But we are targeting at Lyft to use this in production and also fix the issues that need to be fixed on the way. So that is totally the goal. And I think the Python SDK has been around for more than a year, I think now, and there are users on Dataflow. So the Python SDK is not brand new. What is new is the Flink Runner, and we are quite comfortable dealing with the runner issues. Yes.
Okay, second question for me. Here. What kind of data types do you support? Because you're coding and decoding data between different languages, so it's probably not every object, but some kind of data types only supported.
So the answer is all the data types that the SDK or the language supports, because the nice thing is that the runner doesn't actually know what the data is. It is opaque blocks. So for example, if a Flink Runner would like serialized byte arrays, and it just gets them from the harness and sends them over the network and then gives them to the harness again. So for Python, I don't know actually what they support, but I think they are pickable objects. Yeah. And for Go, there is some code-generated serializers, but Beam has this concept of coders that are used for encoding and decoding data. And if you have a data type and you can write a coder for that data type, then you can use that data type. And that is just responsible for encoding it to a byte array and decoding it from a byte array.
That's right. So you can basically optimize how your objects are encoded by writing a highly performant custom coder. Yeah.
Okay, so we don't really have enough time for more questions, but I'm sure Aljoscha and Thomas will be around for any private questions.
Yes.
So
yeah.
thank you.